In the last video, we ended on this rule. It was multiplication rule for independent events. Now, we said if we have two events, A and B, and they're independent, that means that event A doesn't influence the event B, and event B doesn't influence event A. So they are independent. If these two events are independent, then the probability of A and B occurring is equal to the probability of A times the probability of B. Now, we had a rule that was the probability of A or B. When we said the word or, it became addition. Now, when we say the word and, it becomes multiplication. Now, the rule with or was A and B had to be mutually exclusive or disjoint. That meant they had nothing in common. Independent is not the same thing as mutually exclusive. Okay, this means something completely different. And in order for us to use this rule, we have to have independent events. Okay? So again, or becomes addition and becomes multiplication. Let's look back at this example we went through in the last video. We said let A be the event that the first roll is a 3, and let B be the event the second roll is odd. And here what we're doing is we're rolling a die twice. So we roll a die twice. A is the event the first roll is a 3, and B is the event the second roll is odd. What is the probability of A and B? So these are independent events. The first roll doesn't influence the second roll. So the probability, now let's focus on the first roll. If I roll a die, getting a 3, the probability is 1 out of 6. While on the second roll, just focus on the second roll, there's 6 options. Getting an odd number is 3 out of 6. So multiply those two together because we say the word and, we get 3 out of 36, which simplifies to 1 out of 12. Let's look at some more examples of independent events. Suppose we flip a coin twice. We let A be the event the first tosses a heads, and B is the event the second tosses a tails. Notice that when we flip a coin 2 times, the first toss doesn't influence the second toss. So these are independent events. If I want to know the probability of A and B, so that is getting a heads on my first toss and getting a tails on my second toss, then I just multiply the two individual probabilities. The probability of getting a heads on my first toss is 1/2 because there's 2 options, tails and heads, and only one of them is a heads. And the probability of getting a tails on my second toss is 1/2. So multiplying those together, we get 1/4 or 0.25. Here's another example of independent events. Suppose we draw 2 cards from a 52 card deck with replacement. Now, what does with replacement mean? That is, when we draw one card, we're going to look at it, and then we're going to put it back in the deck, shuffle those cards around, and then draw a second card. So that means we're replacing, with replacement means we're replacing that card, putting it back in. So whatever I get on my first draw is not going to affect the second draw. Okay, so suppose we draw 2 cards from a 52 card deck. Let A be the event, the first draw is a queen, and let B be the event, the second card is a queen. What is the probability of A and B? So the probability of A and B, which is both cards are queens, is 4 out of 52 times 4 out of 52. That's because and becomes multiplication, and we think about the first card. There are 4 queens out of 52. That 4 out of 52, the first one, is for the first card. And then the second 4 out of 52 is for the second card. You can get 4 queens out of 52 cards. So if you multiply that together and simplify, you get 1 out of 169. Again, don't worry too much if you have trouble with simplifying fractions, but what you should do, you could put 4 out of 52 times 4 out of 52 into your calculator and see what the decimal is, and it'll be the same as 1 over 169. How I'm getting 1 over 169 is 4 out of 52 simplifies to 1 out of 13. So you get 1 out of 13 times 1 out of 13, and it'll give you this 1 over 169. Suppose we have a hat with the numbers 1 through 10 in it, and we're going to draw a number out of the hat 3 times with replacement. So you see the words with replacement? That means each time we draw a number out of the hat, we put it back into the hat. My first question is, how many different outcomes are there in the sample space? So it would be quite difficult to write them all out and then count them, right? Because if you think about it, we have 3 numbers we're drawing out. So for example, let's just start writing them. The first one could be the number 1. The second draw could be a number 1, and the third draw could be a number 1. Then we could do 1, 1, 2. First is a 1, the second one is a 1, the second one is a 2. 1, 1, 3, 1, 1, 4, 1, 1, so on. And then you can start changing the first 2 numbers, like 1, 2, 1, 1, 2, 2. There's going to be a lot of different numbers. So sometimes it's difficult to write them all out. Is there an easier way to just count them all? So what I'm going to do is I'm going to think about my 3 draws and how many different options I have for each draw. Now my first draw, I have 10 options. My second draw, I have 10 options because we're putting these numbers back into the hat. And my third draw, I have 10 options. So I multiply 10 together with 10 and 10 to get 1,000. If I was to write them all out, I would have to write 1,000 different combinations. So that's going to take you a long time to write them all out. So it's easier just to count them all with this multiplication rule. Now, if we draw a number out of the hat 3 times with replacement, what's the probability that your first draw is a 3, your second draw is an even number, and your third draw is a number bigger than 7? We could try to find all of the different combinations, right? We could do 3, 2, 8. That would be one of the numbers in one of the combinations, right? Because the first one's a 3, the second one has to be even, so 2 is even, and a number bigger than 7, 8. Then we could do 3, 2, 9. Or we could do 3, 4, 9, but that's going to take us a little bit of time to write them all out. Maybe we can use the multiplication rule for independent events here, because when we're putting those numbers back in the hat, we're using the word and here, and they're independent because my first draw doesn't affect my second draw, and that doesn't affect my third draw because we're putting all these things back in the hat each time we draw. So getting a 3, let's focus on the first draw. The probability that if I take a card out of this hat with a number 1 through 10 in it, the probability of getting a 3 is 1 out of 10. So that is my first draw, 1 out of 10. The second draw, an even number. Half of the numbers are even, so that's 5 out of 10. Getting a number bigger than 7. Well, the numbers 8, 9, and 10 are bigger than 7, and that's 3 out of 10. So, because these are independent events, and you have to use the word and in between them, I want to draw a 3 and an even number and a 7, then we use multiplication, and we get 15 out of 1,000. 10 times 10 times 10, that's how many outcomes we have. We said we had 1,000 outcomes. So there's 15 ways to do it out of 1,000. So we have a 1.5% chance. If you put this in the calculator, you'll get 0.015. So there's a 1.5% chance of getting this specific combination. Now, if you don't believe me, I went ahead and listed them all out. Let's count them. So I got 3, 2, 8, 3, 2, 9, 3, 2, 10, 3, 4, 8, 3, 4, 9, 3, 4. These are all the combinations. And it's 5 times 3, or there's 15 ways out of 1,000 to get these combinations. All right, let's try another one. Suppose you draw 3 cards from a standard 52 card deck with replacement. What's the probability of drawing a red card, followed by a diamonds card, followed by a 7 card? Pause the video and see if you can find this probability. Okay, these are independent events, right? We're putting the cards back into the deck because we're doing with replacement. So we think about the first card, it needs to be red, 26 out of 52 for red, then followed by a diamond, that's 13 out of 52 are diamonds. 7 card, 4 out of 52 cards are sevens. So you just multiply that together. I simplified here and I got 1 over 1 over 104. The decimal should be the same if you didn't simplify. So the last topic in this video is the at least one rule, at least once rule. So remember that we said that the probability of an event plus the probability of its complement is equal to 1, which we can rewrite as the probability of an event is 1 minus its complement. Suppose we roll a die twice. What's the probability of rolling at least 1 6? Okay, so rolling a die twice has 36 different options. To get at least 1 6, there's a hard way to do it, which is to count all the different ways we could get at least 1 6. So I could get 6 6, I could get 6 1, 6 2, 6 3, 6 4, 6 5. Or I could do a 1 first and then a 6, a 2 and then a 6, 3 and a 6, 4 and a 6, 5 and a 6. So it looks like there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 different ways to get at least 1 6. So 11 out of 36 would be the probability. Can we solve this problem without counting everything? So here's the second option. Let's think about the opposite of this event, the probability of rolling at least 1 6. The opposite is rolling no sixes. And that probability, that would mean if we're rolling a die twice, the first one is not a 6 and the second one is not a 6. So the first one being a number other than 6, that's the probability of that is 5 out of 6. And the second one being something other than a 6, the probability is 5 over 6. So we get 25 out of 36. And now we're going to use this rule at the top. The probability of A is 1 minus the probability of its complement. So the probability of rolling at least 1 6 is 1 minus the probability of not rolling a 6. And we get the same thing we got in the last problem or the last option, which was 11 out of 36. Let's try another one. Suppose we draw 2 cards from a 52 card deck with replacement. What's the probability of drawing at least 1 clubs card? Well, let's think about the opposite of at least 1 clubs card. That would mean no clubs. So if we're going to draw 2 cards from a deck and not get any clubs, there's 4 suits. So 3 out of 4 suits are not clubs. And so we would want no clubs for the first draw and no clubs for the second draw. And we'll get 9 out of 16. And then to get what we want, which is drawing at least 1 clubs, we need to do 1 minus 9 out of 16. So 1 minus the complement, and we get 7 out of 16. The last thing I wanted to say about independent events is that, and we saw this, it doesn't matter how many events you have, as long as they're independent. If you want to find the probability of A and B and C, if you had and D and E and F, they're just multiplying all those events together. And that will give you the probability. So the probability of each individual event, just multiply them together. As long as they are independent, all of them are mutually independent. And then the last thing I want to talk about, which is going to bring us to our next video, is dependent events. We're going to see this topic in more detail in the next video. which is what is an example of a dependent event and how do we find probabilities involving dependent events? So here's an example of a dependent event. We draw a card from a 52 card deck, then we put it off to the side, and then we draw a second card. And then I ask you something like, what's the probability of getting two diamonds cards? Well, the fact that we put one to the side, that means we have less cards in the deck. And so that is going to affect the probability of the next card. So the first event affects the second event. So then they won't be independent because independent means one event does not affect the other. So when we put a card off to the side, this is called drawing cards without replacement. Another example of dependent events is rolling a die twice, and A is the event you roll a 5, and B is the event the sum of the two rolls is a 7. Here, the event B is taking into account what A is, so we would have to use a different formula in order to figure out that type of probability.